All right, well, thank you. Yeah, big thanks to the organizers for inviting me, and also a big thanks for scheduling my talk after Henry's, because it will be very convenient having everyone already seen a lot of the background involving pseudorandom states. It says UT Austin here, but today is actually officially my last day as a student at UT Austin, so in a couple weeks I'll be starting as a postdoc at the Simons Institute at UC Berkeley. So I'm going to get started on talking about this work, which is kind of based on understanding what are the minimal computational assumptions that we need to build computationally secure quantum cryptography. This is based on joint work with Lowen Chen, Makran Sinha, and Avishai Tal. And let me first explain to you what the title means. Presumably many of you already know, but for those of you who don't, the title refers to one of the 5 worlds that were introduced in an influential survey by Vassal and Pagliazzo in the 1990s. This is a survey about average case complexity surrounding the P versus NP problem. And Pagliazzo basically put forth that there are 5 possible resolutions to the P versus NP question that have interesting practical consequences in the real world. And these 5 resolutions range all the way from Algorithmica, where P is equal to NP, and so a wide range of computational problems can just be solved efficiently in polynomial time, all the way down to Cryptomania, where P is different from NP in such a strong sense that you actually get really powerful cryptography, like public key encryption, for example. And if you're a classical cryptographer, you generally hope that we live somewhere below this line in either mini-crypt or cryptomania. And the reason for this is that what characterizes whether you are above or below this line is the existence of a fundamental primitive in classical cryptography, namely one-way functions. And well, I guess I can take you to the next slide. So presumably many of you have seen one-way functions before, but for those of you who haven't, informally, a one-way function is just a function that is easy to compute, but it's hard to invert. So you can compute it in polynomial time, but any polynomial time adversary given f of x for a random input x cannot efficiently find a pre-image under that function with better than negligible probability. And the reason why classical cryptographers like one-way functions so much is that they turn out to be both necessary and sufficient for lots of classical cryptography. So indeed, for basically any super polynomially computationally secure quantum cryptography, it has been shown by a series of reductions that the existence of pretty much any primitive implies one-way functions in a black box fashion. And conversely, it also turns out quite remarkably that one-way functions also suffice for a lot of cryptography, including things like pseudorandom functions, digital signatures, and commitment schemes, to name a few examples. And we have this really beautiful theory in the classical setting surrounding one-way functions, and kind of the motivation for this talk is to understand what happens in the quantum world. So if we allow cryptography that's not purely classical, but that uses quantum information, then are one-way functions still necessary in the quantum world, both in the sense of do we still need one-way functions themselves, or can we build quantum cryptography without one-way functions? And also in the sense of what are sort of the minimal computational assumptions that are necessary in order to build quantum cryptography? And I'm sure many people in the audience would think about this question for just a little bit and immediately come to the conclusion that, well, actually, in a way, no, we really don't need one-way functions in the quantum world. We have these cryptographic protocols, such as the BB84 quantum key distribution or Wiesner's quantum money scheme, that are actually unconditionally secure. So the proof that these things are secure is information theoretic. So in quantum key distribution, for example, 2 spatially separated parties can securely exchange a random key over an unsecured quantum channel in a way that is impossible to break, assuming the laws of quantum mechanics. And similarly, in Wiesner's quantum money scheme, again, the proof is information theoretic. And also, remarkably, it achieves something that's even impossible to achieve classically, namely quantum banknotes that are impossible to physically counterfeit. And so, there's already some evidence that in the quantum setting, something is different because we have these sorts of protocols that, provably achieve something that you cannot do using classical information alone, and whose proofs are unconditional. They do not rely on unproven computational assumptions like P is different from NP or the existence of one-way functions. But unfortunately, this is not the end of the story. Indeed, if this were the end of the story, this would be a pretty boring talk. Indeed, most computational tasks actually require some form of computational bound on the adversaries that you consider. So for most cryptography, you can show, by more or less complicated proofs that you cannot have just information theoretic constructions of these primitives, including things like symmetric key encryption, commitment schemes, and digital signatures, which are these sort of mini crypt primitives that we can build classically from one-way functions, but also these stronger kind of inherently quantum primitives like publicly verifiable quantum money and quantum copy protected software, where again, we can show that you can't hope to build these using purely information theoretic tools. And so this kind of motivates us to, study, okay, what sorts of computational assumptions actually suffice to build quantum cryptography? And if you saw Henry's talk earlier today, which I'm sure many of you did, one thing that this motivated people to define is to say, let's kind of try to define like quantum analogs of one-way functions or pseudo-random generators and see if, perhaps A, can we build interesting cryptography from them? And B, can we perhaps show that these things might be, in some sense, more fundamental than one-way functions? Like, are these more of a minimal assumption for quantum cryptography? And I'll start with the definition of pseudo-random generators, which we saw in Henry's talk. Informally, it's just a keyed ensemble of quantum states with the property that, first of all, you can efficiently generate copies of the state given a key in 0, 1 to the kappa. Kappa is like the security parameter. And for all polynomial time adversaries and any polynomial number of copies, the adversary cannot distinguish copies of that quantum state from copies of a hard random state with better than negligible advantage. And indeed, this is quite similar to the definition of classical pseudo-random generators with basically only two differences. One, that rather than just trying to mimic the uniform distribution over n-bit strings, we're trying to mimic the uniform distribution over n-qubit quantum states. And two is that in general, we will allow the adversary to have access to any polynomial number of copies of the state. And this is kind of justified by the quantum no cloning principle, where there are things that you can do with many copies of a state that you can't just do with one copy because it's impossible to clone an unknown quantum state. But nevertheless, it turns out that you can actually define a version of pseudo-random states where actually the adversary only gets a single copy of the state. So this is not something that we saw in Henry's talk. But there's basically just one extra criterion you have to add, which is that the pseudo-random generator needs to have stretch. So in other words, it needs to map a shorter kappa bit seed to a longer n-qubit quantum state. And this is, not really for any special quantum reason. This is completely analogous to how for classical pseudo-random generators, you need to map, a shorter seed to a longer string. So it's sort of just to prevent like a trivial solution to this problem of just like outputting basically the maximally mixed state. This just guarantees that like this distribution over quantum states is always far from the maximally mixed state because it is over like a strictly smaller subspace. And we like pseudo-random states and even these single copy pseudo-random states for a lot of reasons. From my view, there's kind of three main reasons that motivate their construction. The first is that they suffice for a wide range of these cryptographic primitives, as we saw earlier, including things like commitments, digital signatures, some forms of multi-party computation, and zero knowledge. A lot of these are basically these, these mini crypt primitives that we can otherwise build from one-way functions. The second is that they are actually implied by the existence of quantum secure one-way functions, as was shown in the very same paper in which they are first defined. And so if you believe that one-way functions exist, you should certainly believe that pseudo-random states exist. So they are no stronger a computational primitive than quantum secure one-way functions. And indeed, there's actually some evidence, some heuristic evidence to suggest that pseudo-random states are in some sense a perhaps a more fundamental or weaker assumption than the existence of one-way functions. But this point is actually kind of subtle, and before this work, we really only had one piece of evidence in this regard, and I want to kind of go a little bit into detail about what that evidence was. And what it was this result of mine, actually, from a little over 2 years ago, where I showed that there exists a quantum oracle, meaning a unitary transformation that you can query as a black box in a single step, with the property that, first of all, BQP is equal to QMA relative to this oracle. So any problem that you can solve by QMA is like the quantum version of NP. So like the quantum version of NP actually collapses to polynomial time quantum algorithms, at least by any algorithm that queries this oracle. And yet, nevertheless, pseudo-random states also exist relative to this oracle, meaning that there's an algorithm that generates an ensemble of states querying this oracle, but you can show that any adversary, any polynomial time adversary, needs to make a super polynomial number of queries to the oracle in order to break that pseudo-random ensemble. And this is kind of, in a way, saying that we can have pseudo-random states without one-way functions. And so why is that? Well, if BQP equals QMA, that implies that BQP contains NP. So in other words, a quantum computer can efficiently solve NP problems. And if you can efficiently solve NP problems, then we know by pretty simple reductions that you can break one-way functions. So in some sense, this is saying that like in this oracle setting or this black box setting, it is possible to have pseudo-random states without one-way functions. In this restricted black box setting. And I should note that like by contrast, the proofs that say P equals NP implies that one-way functions do not exist, those hold relative to every oracle, right? So those are what we call relativizing proof techniques. And so what this is sort of saying is that there's no quantum relativizing proof technique that establishes that pseudo-random states imply one-way functions. Whereas conversely, we know that one-way functions do imply pseudo-random states. So in some sense, pseudo-random states are perhaps weaker than one-way functions. Unfortunately, this prior work of mine comes with what I think are kind of three major caveats to interpreting this result as giving rise to some separation between pseudo-random states and one-way functions, which I want to now briefly go over. The first is that in some sense, it's kind of cheating to use a quantum oracle to establish the separation, kind of for trivial reasons that since one-way functions are a classical cryptographic primitive, there's no way to define classical queries to a quantum oracle. So it's sort of just for trivial reasons, you can't have one-way functions that non-trivially depend on the oracle. And perhaps it's unsurprising then that you can, with a quantum oracle, do some quantum primitive, but not a classical primitive. And you can arguably get around this by kind of modifying the definition of one-way functions to be to allow them to be computable by quantum algorithms. But there's some bigger problems, including the fact that just conceptually, quantum oracle separations are weaker than classical separations. And what I mean by that is that the set of proof techniques that hold relative to every quantum oracle is a strict subset of the set of proof techniques that hold relative to every classical oracle. This was observed by Scott Aronson in, I think, 2009. And so this is kind of saying that maybe the fact that we had this black box separation is just a consequence of the fact that we're using this weird quantum oracle that's like a unitary transformation that you can query. Maybe if we restricted ourselves to classical oracles, you would not be able to get this kind of a separation. And then finally, what in my view is perhaps the biggest problem, while this does give some sort of black box separation, it doesn't really give us any insight into how we might conceivably instantiate pseudo-random states in the actual world without relying on one-way functions. And sort of the reason for this is that the construction of this oracle involves choosing literally a Haar random unitary oracle. So like literally a random unitary transformation in the black box. And the problem is that we very much do not know how to model random unitary oracles in the unrelativized world. By contrast, we do know how to model random Boolean functions. So you may have heard of the random oracle heuristic, or like the Fiat-Shamir transform, where for a variety of cryptographic primitives, if you can show that they are secure relative to some random Boolean function, then plausibly, if you replace that random oracle with some, your favorite cryptographic hash function like SHA-3, then that should give you a secure instantiation of that primitive, in the actual world. And this is, a well-tested computational assumption that has been studied for decades. And kind of my point is that we don't have like a quantum SHA-3, as far as I know. Like there might be some heuristics that people have come up with to kind of model random unitary transformations, but we very much don't really know, I think, how to, appropriately model like a quantum hash function or something like that. So, so while this work is saying that in some sense pseudorandom states are possible without one-way functions, it has a lot of caveats. And I think the short summary of this work is that we basically address all of these caveats simultaneously. And let me explain to you exactly what we prove. So we introduce a new cryptographic security property of a concrete hash function, a classical hash function, that satisfies the following three nice conditions. First of all, assuming that this property holds, then you actually get pseudorandom states. So it suffices to construct single copy pseudorandom states, and thus by known reduction suffices to construct a wide range of interesting cryptography, including things like some form of digital signatures and commitment schemes. Second off, it actually holds for a uniformly random classical oracle. So if you believe in the random oracle hypothesis, then plausibly, if you replace the random oracle with your favorite cryptographic hash function, this should give rise to a secure instantiation of pseudorandom states. But then finally, and most interestingly, we show that in the black box setting, this property is independent of the P versus NP problem. So in other words, you can construct black boxes relative to which P is different from NP, and yet the security property holds. And you can also construct black boxes relative to which P is equal to NP, and yet this security property still holds. So another way of saying this is that we construct an oracle relative to which P is equal to NP, and yet we still have pseudorandom states. So in other words, if we kind of go all the way back to slide 1, what we're basically saying is that all the way up here, all the way in Algorithmica, where classical cryptography is essentially unthinkable, it is actually still consistent with our knowledge that we could have computationally secure quantum cryptography based on pseudorandom states, which is quite surprising, I think. So there's some world where we basically need to fire all of the classical cryptographers and hire quantum cryptographers instead. So are there any questions about these results? Okay. I guess if not, then in the time that remains, what I want to do is I want to first explain to you what this cryptographic security property is that we introduce. I want to explain how you build pseudorandom states from it and why it satisfies all of these nice properties, like it's independent of the P versus NP problem, and tell you just a little bit about some of our proof techniques. And then finally, I will conclude with some of my favorite open problems. So let me first start by defining this cryptographic property, which we will think of as, our hash function, big H, we will think of as defining a bunch of sub-functions that we will call f sub k and g sub k for each of the k's in, in our set of seeds 0, 1 to the kappa. So we have like a pair of n-bit Boolean functions for each k. And the security game that defines the security property of this hash function is the following. You are given black box access to an auxiliary function, little h, in fact, actually quantum black box access, so you can query it in superposition. And given access to this function h, you must distinguish the following two cases. First, decide whether h is a uniformly random Boolean function, or two, whether there exists some key k in 0, 1 to the kappa, such that h is non-negligibly correlated with the Boolean Fourier transform of fk multiplied pointwise with gk. So one thing to point out is that this is kind of analogous to the definition of pseudorandom functions. Okay, I guess I should add. So the security property is that it should be hard to distinguish these two cases with better than negligible advantage by polynomial time adversaries. And this is kind of analogous to the definition of pseudorandom functions, where you want to distinguish a random function from a pseudorandom function given query access. But now there's sort of a different notion of what it means to be pseudorandom. So rather than just directly drawing the pseudorandom function from the hash function, you're drawing the pseudorandom function in some weird correlated fashion that involves a Boolean Fourier transform. So that is the security property. How do you build pseudorandom states from this? That turns out to be actually even easier to describe. So the way you build pseudorandom states, so you'll have a pseudorandom state keyed by each of these keys k, and the pseudorandom state keyed by k is just the following. You start in the L0 state, you Hadamard all of the qubits, you query fk in superposition as a phase oracle. So on input ket x, you just apply a plus or minus 1 phase according to f of x. Then you Hadamard all of the qubits again, and then you query gk in the same fashion as you queried fk. And this is the pseudorandom ensemble. So it's pretty simple to describe. And for those of you who know a little bit about quantum query complexity, it might not surprise you that everything I've been talking about so far is secretly some version of the correlation problem in disguise. So what is the correlation problem? Well, this is a problem in quantum query complexity that was introduced by Scott Aaronson in 2009. And it does the following. So you're given a pair of Boolean functions, f and g, n-bit Boolean functions as a black box. And you must decide whether f and g are both uniformly random Boolean functions, or whether the Boolean Fourier transform of f is non-negligibly correlated with g. And in the paper in which this problem was introduced, Aaronson observed that this problem admits an efficient quantum algorithm. So in other words, the correlation problem is in BQP. And in fact, actually, depending on how you define this problem, you can even solve this problem using just a single query to both f and g. And indeed, the algorithm that solves the correlation problem turns out to essentially be this circuit with like a layer of Hadamard measurements at the end. So you can always see some connection to correlation. And the reason Aaronson introduced this problem was as a candidate for a problem that might separate BQP from this other complexity class called pH, or the polynomial hierarchy. And hopefully some of you have seen pH before, but for those of you who haven't, it's sort of like a closure of NP under efficient reductions. And it roughly corresponds to the set of computational problems that we could solve efficiently for free if it turned out that P collapsed to NP. So, and yeah, the correlation problem turned out to actually be the first problem that had this property, that it was contained in BQP, but it was not contained in pH. So what is the relevance of the correlation problem to our question? Well, it turns out that we actually need a stronger property that was proved by myself with Scott Aaronson and Devon Ingram just last year, that a problem called OR of correlation is not contained in this complexity class BQP to the pH. So let me break that down a little bit. What is the OR of correlation problem? Informally, what it is that you are given a long list of instances of correlation, and you must decide whether all of the pairs of functions are uniformly random, or whether there exists some pair of functions in this list that is in fact correlated. So that's why it's like the composition of the OR function with correlation. And what is this BQP to the pH class? So that that denotes BQP with an oracle for pH. And informally, this corresponds to the set of problems that you could solve efficiently on a quantum computer if it turned out that P collapsed to NP. So that's kind of the connection back to the independence from the P versus NP question. Basically, if you can show that something is secure in this P to the pH model, then you can sort of show that the hardness of this property is independent of the P versus NP question. And I'm going to be a little bit hand-wavy here, but informally, what ends up happening in our security reduction is that we just observe that this security game here of distinguishing random H from an H that's sort of correlated in this funny fashion, it turns out that you can actually just view it as some instantiation of this OR of four relations problem. So that's what's going on, and we're basically using this hardness result that was established in this earlier work and turning it into a new cryptographic lower bound. Let me briefly also say a few words about how you go from, I guess, this security property to showing that the pseudorandom state ensemble is secure. So like a lot of things in quantum cryptography, this proceeds via a hybrid argument, where at the top we have the first hybrid, which is just a state drawn from this ensemble for a random key k. And at the bottom we have the Har-random ensemble, where you have just a uniformly random n-qubit state. And there are these two intermediate hybrids that both involve these quantum phase states, so what I denote by capital phi sub h, which just means the uniform superposition over all n-bit strings x, where the phase on that superposition is like a binary plus or minus one phase that is chosen according to the function little h. And so the intermediate hybrids are a phase state for an h that satisfies this correlation property, and a phase state for h where h is uniformly random. So how do we show that these hybrids are all indistinguishable? I guess I'll work bottom up because that's kind of the easiest way. So showing that these last two hybrids are indistinguishable is actually the easiest part. In fact, they're just information theoretically identical. And you can basically show that for single copy pseudorandom states, they're both just identical to being handed the maximally mixed state. So that's pretty simple. Showing that hybrids 2 and 3 are indistinguishable, this turns out to basically be equivalent to this security property of, since we're positing that it is hard to distinguish an H that's random from an H that's correlated in this funny fashion, then certainly if you're just given a state that has H in the phases, then those should also be hard to distinguish. And again, that kind of works via reduction to this OR of four relations problem. And then finally, that just leaves showing that hybrids 1 and 2 are computationally indistinguishable. And that turns out to be kind of the most tricky. So to get this to work, we actually had to be very careful in defining what it means to sample an H that is correlated in this fashion. And in fact, we had to define like a new variant of the four-relation problem and basically reprove everything applied for this variant of the four-relation problem that we defined. And the argument itself is also a little bit subtle because you don't directly show that H2 and H1 are indistinguishable. What you actually show is that H2 is like statistically indistinguishable from a probabilistic mixture of H3 and H1. And then using the fact that H2 and H3 are indistinguishable allows you to conclude that H1 and H2 are indistinguishable. So it's kind of a subtle argument, but that's the rough overview of the proof. I will say that like the number one question that I usually get about this work is actually people tend to ask me like, what is the intuition for why this OR four-relation problem is hard for BQP to the pH? And I do have a bonus slide at the end if people are interested, because it's a little bit technical, so I don't want to go into it. But if people are curious, I can say at least a few words about how that proof proceeds. So that summarizes everything I wanted to say about the proof techniques. In my remaining time, I'm just going to briefly go over some of my favorite open problems on the subject. Starting with maybe the most natural question, which is, can we extend our proof to a proof of multi-copy security? So in other words, can you get multi-copy secure pseudorandom states rather than just these single copy states? And we show that actually assuming a plausible conjecture about a generalization of the correlation problem, you actually can extend our proof techniques to show security in the multi-copy setting. One thing I should also clarify is that we do not show that our construction is insecure in the multi-copy setting. It's just that our proof of security breaks down in the multi-copy setting. But actually, I think I would even conjecture that even the same construction should still remain secure even with many copies. I guess a second natural question is kind of whether we can qualitatively strengthen this result to one where not just P is equal to NP and PRSs exist, but one where perhaps P is equal to QMA. So like the quantum analog of NP is easy and pseudo-random states exist. And again, previously we could only sort of do this with a quantum oracle. Whether we can do this with a classical oracle is, I think, a nice open question. And then finally, I think the last question I have that is a little bit, maybe harder to motivate, but I really want to understand like whether single copy pseudo-random states or any of these kind of more basic quantum cryptographic primitives still imply some classical lower bound in complexity theory. Like, for example, P is different from P space. Or is it conceivable that one could show the existence of pseudo-random states unconditionally without like proving some breakthrough lower bound in classical complexity theory? Yeah, I think this is like my favorite open question. And I guess that's about everything I want to talk about. So I think with that, I'll stop here and I'd be happy to take any questions.
Okay, thank you, William. Questions? Hi. In the proof sketch that you showed, like where does the proof fail when you try to prove multi-copy PRS? Like you said, you might have to change the construction.
Good. The step that fails is the statistical indistinguishability of hybrids 1 and 2. Or rather, this step where I argue that like hybrid 2 is like somehow a mixture of hybrids 1 and 3, that fails in the multi-copy setting. Those are no longer statistically indistinguishable. They might still be computationally indistinguishable, but it would have to be for different reasons.
I see. So, and can you say a bit like how do you actually change the construction to fix this? You said like if you have a T4 relation, then you can.
Yeah. So you basically have to add more functions and more layers of Hadamard gates. Well, okay, it depends. Like so like in T4 relation, you have not just 2 functions but T functions, and you have a circuit that looks like this where you alternate, Hadamard queries, etc. And yeah, like if you have this statistical property for relation for some T, then you get pseudo-random states with that construction of T.
And like, will the number of copies depend on this T, or it would be for any polynomial?
At least under our conjecture, the number of copies would not depend on T.
Yeah. Great. Thank you. More questions?
Could you say or give some intuition for why so you use this like leverage this powerful result about separating BQP from pH. Why pH? Was that really? Do you think it's necessary, or it was just what was available for you to leverage?
Yeah, like again, it's like pH because we want like we want security like even if P equals NP, and intuitively pH is like again the set of problems that you can solve efficiently if P equals NP. So somehow by showing security against, but by showing that aura-correlation is hard for BQP to the pH adversaries, there's a way to turn this in like a fully black box fashion into like some different problem being hard for BQP adversaries while simultaneously collapsing P to NP. So there's a way you just like add some stuff to the oracle in like a completely deterministic way.
Mm-hmm.
Yeah,
that makes sense. All right, thanks.
Okay, more questions? There's plenty of time. So I have a question.
Mm-hmm.
So in your earlier work, you showed that pseudorandom states exist relative to a ha-random unitary oracle. Do pseudorandom unitaries exist relative to such an oracle?
That's true. So like this result, even though I only mentioned pseudorandom states, it also achieves pseudorandom unitaries with the same result. And yeah, it's actually, I mean, it's still open to construct pseudorandom unitaries relative to any classical oracle. So yeah, as far as I know.
Okay, I get to ask another question. So you talked about the 5 worlds, and it seems like the 3 sort of settings that we've mostly been talking about so far is cryptomania, where public key crypto exists, mini-crypt, where symmetric key crypto exists, and then kind of everything else.
Yeah.
So do you think there's anything interesting to say about like the distinction between Algorithmica, Heuristica, and Pessoland with respect to quantum crypto?
I mean, that's a good question. So like, I know a couple of people have asked me this question of like, you know, could we conceivably base quantum cryptography on, one-way functions maybe are too strong. Like, what if we just assume that like NP is hard on average or something, or that P is different from NP? Could we get cryptography from that? I think that's a really interesting direction. Personally, I think I'm not that optimistic that that would be very easy, but it might be possible. But I guess also like another message of this work, from like a completely different perspective, is kind of saying that like, the quantum version of these pictures looks very different. Like, yeah, in Pagliazzo's 5 worlds, it doesn't really, somehow the analogies break down more in the quantum setting than in the classical setting. And it might not be such a clean picture.
So maybe we need a different set of worlds for quantum?
Yeah, I mean, maybe. Again, a lot of it is that we don't really know, like, classically we have all these things that are equivalent to one-way functions. Like quantumly, we don't seem to have that. So yeah.
Okay, any more questions? Okay, if not, let's thank the speaker.
Thanks.